Welcome to The Explainer. Today, we're diving into something absolutely wild, the fascinating microscopic journey of how your data travels across the globe in literally the blink of an eye. Have you ever stopped to think about how a massive, high-res photo on your phone just zips across the world to a friend in milliseconds? And it does this without crashing the internet. It feels like magic, right? But it is actually this incredibly orchestrated system of data transmission. So here's our roadmap for today. First, the magic of data packets. Second, routers and packet switching. Third, serial versus parallel transmission. Fourth, simplex, half, and full duplex. Fifth, the universal serial bus. And finally, a quick test of your knowledge. All right, section 1, the magic of data packets. You see, we don't just blast one giant stream of data across the web. Instead, we chop it up into smaller, super manageable chunks called data packets. To put that into perspective, a standard smartphone photo is broken down into over 70 individual packets. By keeping them tiny, usually around 64 kilobytes, the network becomes incredibly efficient and totally resilient against dropped connections. It's kind of like moving a mountain one bucket at a time. Think of a single data packet exactly like a physical package you'd send in the mail. The header acts as your shipping label, packed with the sender and receiver IP addresses and a sequence number. Then you've got the payload, which is the actual contents or data chunk. And finally, the trailer is basically a security seal. It uses a mathematical formula to make absolutely sure no data was corrupted during the trip. Moving on to section 2, routers and packet switching. So our packet is boxed up. Now think of a router as a highly caffeinated postal worker, sorting mail at an intersection, deciding exactly where your package needs to go based on real-time traffic. The internet isn't just one straight wire. It's a massive web of intersections called nodes. When a packet arrives, the router checks that destination IP in the header and independently calculates the absolute shortest, least congested path forward. Let's actually see this in action. Imagine our single packet has just left computer A. It hits the very first network intersection at node R1, and it's looking for the fastest route out of there. Instantly, R1 realizes, hey, the usual path is totally jammed up today, so it bounces our packet over to node R3 to avoid that network gridlock. This right here is the true beauty of the system. Because your file is broken into thousands of independent packets, if a cable suddenly gets cut or a node is overwhelmed, the routers just simply reroute the remaining packets down different paths. That is packet switching in a nutshell, bouncing over to node R4 and finally arriving safely at computer B. Now, because these packets take all sorts of crazy different routes, they often arrive completely out of order. But remember that sequence number in the header we talked about? Well, computer B uses that to seamlessly piece everything back together into the original photograph before you even notice a thing. Next up, section 3, serial versus parallel transmission. Now let's look at the actual physical highways these packets travel on. We've got serial and we've got parallel. Serial transmission sends data one bit at a time over a single wire. It's single file, meaning bits arrive perfectly synchronized, which makes it incredibly reliable for long distances. Parallel transmission, on the other hand, blasts multiple bits simultaneously over several wires. It's super fast, but over long distances, those bits travel at slightly different speeds, causing something called data skewing. That's exactly why parallel is strictly reserved for those tiny, short distances inside your computer's internal circuits. All right, section 4, simplex, half, and full duplex. We have the roads, but now we need the traffic rules. Simplex is a strict one-way street, perfect for sending a document to a printer. Half duplex is like using a walkie-talkie. You have to take turns talking and listening. But full duplex, that is what makes modern life possible. It allows simultaneous two-way traffic. It's the whole reason you can game online with your friends while receiving their video and audio feeds without a single hitch. Moving along to section 5, the universal serial bus. You definitely know this one. The USB is an absolute powerhouse, and it relies on a rock-solid serial connection. Inside that standard shielded cable, you'll typically find 4 wires. 2 supply power to charge up your device, and 2 handle the data transmission. What makes USB so brilliant, though, is how incredibly user-friendly it is. The very moment you plug it in, your computer detects a voltage change, figures out what the device is, and automatically loads the driver software. Plus, thanks to backward compatibility, you can plug a brand new USB into a much older computer, and it just works. Finally, section 6, test your knowledge. Okay, let's put you in the hot seat with a real-world scenario. Rory is sending data to a server 100 meters away. He needs absolute accuracy over this long distance, and crucially, he must be able to read and write to the server at the exact same time without waiting his turn. So, based on what we just covered about distance, data skewing, and traffic rules, which two transmission methods are his absolute best option? Take a second and think about it. Got your guess? The answers are serial and full duplex. Serial prevents the data from skewing over that long 100-meter gap, while full duplex guarantees Rory can read and write simultaneously. If he'd chosen parallel, the bits would have arrived completely out of sync, totally ruining the file's accuracy. And if he'd gone with half duplex, he would have literally had to sit there and wait for a read operation to finish before he could even start writing. That brings us to a fascinating final thought for you to ponder. If a single file relies on millions of packets hopping across independent global routers, how does your computer know if even a single 0 or 1 gets corrupted along the way? We briefly mentioned the CRC in the packet trailer today, but the way computers actively hunt down and fix corrupted data during transmission is a whole other wild journey. Keep that question in mind, and thanks for exploring this with me today.